Assalamu alaikum and welcome to video 3 of this revision. Again, I am Ms. Fatima Abbas of Al-Fadl School in Yahar, and I will take you through the last bit. Hopefully there will maybe be 2 more videos, but let's go ahead and talk about mechanical waves, and here we're looking at properties of waves. So this outcome says to define amplitude, intensity, loudness, and pitch of a wave and relates to real-life examples. So let's take a quick look at these different properties of the wave. So amplitude refers to the size of the wave. Now we also should remember here that amplitude is proportional to energy. So if we look back to that equation, energy is proportional to amplitude squared. Okay, this might come in handy later, but amplitude is going to be the measure of the height of the wave from 0 to the crest, or the depth of the wave from 0 to the trough. Okay, so that is our amplitude, and I think that is easy enough. So when we say 0, I'm talking about the resting position. We see his hand is right here going through the middle. Okay, now again we can measure amplitude here with our longitudinal wave. So this is our transverse wave, very simple. Amplitude can be measured in our longitudinal wave, again going from rarefaction to rarefaction, or we can measure from compression to compression. And I hope that's, remember, rarefaction is a place where it's stretched. Compression is the place where it's squeezed. Compression, remember, talks about pressing or duct back pressure. The more energy a sound has, the higher the amplitude and the higher the loudness and intensity. So what's the difference between amplitude, loudness, and intensity? Loudness means how we hear it. So loudness is going to be exactly how we perceive the sounds to be. So it's how each individual hears the sound. Whereas intensity is going to talk, or by definition, is the amount of sound energy that passes through a square meter of space, and that unit of measurement for intensity is going to be decibel. But we can also think about intensity as how strong it is. So the decibel is a unit of measure that describes the intensity or loudness of sound. So we can see that there's, of course, a danger zone that we should be all aware of. For example, earbuds at full volume would be within the danger zone of hearing loss. The decibel level of city traffic is about 85 decibels. The level of a rock concert is 105 decibels. So if we take that number, we have 105 minus 85, which is 20. Okay, so this is how we got 20 on the next problem down here. This means a concert which is 20 decibels higher has about 10 times 10 or 100 times more energy than traffic. So what does that mean? 10 squared. We just take that, so 10 times 10 would be 20, so we can use that as 10 squared, which is 100 times more energy than traffic. As sound gets louder, the amount of times you can listen without hearing loss gets shorter. So we don't want to listen to our earbuds at full volume too long, just like we wouldn't want to listen to a garbage truck too long, because they are very loud and can cause damage to our ears. Pitch. Pitch is a perception of how high or low a sound seems. A higher frequency sound, so now we're talking about frequency, a higher frequency sound will produce a higher pitch. So frequency is how many waves we have within a given amount of time. So what I'm drawing here would be a high frequency sound, whereas something like this might be a low frequency sound. So in that same amount of time, we only have maybe one wave. An adult male voice has a frequency, so frequency is measured in hertz, of 85 to 155 hertz. So as I was doing in some of my classes, a low frequency sound would be really low like this, whereas an adult female voice has a range from 165 hertz to 255 hertz. So my high frequency sound would sound more like this. So again, here are our examples. A male voice would have a low frequency sound, and let me switch back to my blue. An adult female voice will have a high frequency sound. So a higher frequency sound would be a higher pitch, and the low frequency sound would be the lower pitch. Okay? So pitch and frequency are directly proportional. The human ear can detect sounds with frequencies between 20 and 20,000 hertz. Frequencies above this range are called ultrasounds. So we have a dolphin with ultrasound hearing sounds more than 100,000 hertz. Blue whales also have ultrasound hearing because they're hearing sounds higher than a human, as well as dogs, gerbils, and bats. Blue whales can also hear sounds lower than a human. So there are sounds that are occurring all the time that are at frequencies above which we can hear, and these are called ultrasounds. Joanie plays a scale on her clarinet as she plays from low notes. So remember, low notes are going to be, let me undo that, let me erase that. So low notes, remember, are going to be like our male's voice, to high notes, which are going to be our female voice. For example, what happens to the sound waves that the clarinet creates? Remember, frequency and pitch are directly related. So low notes are going to have higher or lower frequency. High notes will have higher frequency. So the frequency of the sound waves are increasing as she goes from low to high, because frequency and pitch are related. Amplitude have to do with energy, loudness, and intensity. Again, amplitude and intensity are related, so we'll cross that out. Now we see wavelengths. What we need to know about wavelengths is that they are inversely proportional. So if we have a high frequency sounds, we're going to have a short wavelength. If we have a low frequency sounds, we are going to have a much longer wavelength. So wavelength and frequency are inversely proportional or opposite. So this will not be true, because as it goes from low to high, the wavelength will actually decrease. Now let's look. Here's a simple math connection. The table to the left shows the decibels produced by a number of objects. According to the table, which sound has one that is 1,000 times more energy than a sound of a dishwasher? So I'm going to count zeros. 1, 2, 3 zeros. That means if we put this as an exponent, one way to think of it will be 10 to the third power, which means how many tens do we need in there? We need 3 tens. So we're comparing a dishwasher. We would want something that is 30 decibels away, because we're going to now take that 3 times 10. So when we say 30 decibels away, we know that 90 minus 60 is going to be equal to that 30. So what has 90? That is the lawnmower. And again, this question is directly related to the information we went over here. So hopefully you have some understanding of how I did that math there. Because remember here we had 20, a difference of 20 decibels, so we did 10 squared, or 10 times 10. Here we're moving in the reverse direction. We have 1,000 times more, so that is 10 cubed, and we figure out that cube just by counting zeros. How many zeros do you have? 1, 2, 3. So that's going to be cubed. Then we do 3 times 10. I'm going to write that in there because I kind of skipped steps. That's why I'm a science teacher, not a math teacher. 3 times 10, which gives us that 30. Then I do 60 plus 30, which is equal to 90 here, which gives us lawnmower. Okay. Now looking at wavelength that I went over a little bit, it says find and calculate the wavelength, wave characteristics, so that's wavelength, frequency, and amplitude. Very simple with a transverse wave. We know wavelength is a distance from crest to crest, or it can be from trough to trough. And a longitudinal wave, we're going to go from the distance from the middle of one compression to the middle of the next compression, or from rarefaction to rarefaction. Both are work, right? Frequency is equal to the number of waves divided by the time. So here they give us the time in seconds, and we just count. 1, 2 crests, that means there's 2 waves. 2 divided by 2 is 1 hertz. Here we have 1, 2, 3 waves, 3 crests. 3 divided by 2 is 1.5 hertz. Here we have 1, 2, 3, 4, 5, 6 crests, so 6 divided by 2 is 3 hertz. The amount of energy transferred by wave in a given time is proportional to its frequency. If the frequency of the wave doubles, the energy of the wave also doubles. So wavelength and frequency, this is more practice you can do here. Let's get to some questions. You can express the relationship of wavelength and frequency with ratios. The wave on the left has a ratio of 1.1 to 4. So remember, ratios are similar to fractions. For every 1 wavelength, 4 seconds pass. What would the ratio be for 2 waves that travel in 12 seconds? So we can write it as a simple fraction first. 2 over 12. We can then simplify this fraction. 2 goes into 2 Let's write the equivalent fraction. 2 goes into 2 one time. 2 goes into 12 6 times. So that's 1/6. And now we can write it as a ratio, which is 1 wave to 6 seconds, or 1:6 ratio. Okay, so we spoke about types of waves. Just know that water waves in the ocean are both transverse and longitudinal waves. Okay? Let's look at this one right here where we can determine the wavelength, frequency, and amplitude. Okay, let's start with looking at wavelength. Wavelength is fairly easy. We're going to measure from here to here. So halfway between 0.5 and halfway between 1.5 and 2. So this is going to be a wavelength of 1 meter. We can do the same thing here. Or let me just focus on this. Then we have, I'm going to erase this. Now we can look at frequency. We have, count the waves, 1 crest, 2 crests, and 4 seconds. So we do 2 divided by 4, which is equal to 1/2 or 0.5. So we have a frequency of 0.5 hertz. Sorry, it's hard to control the pen there. So wavelength of 1 meter, frequency of 0.5 hertz. Now let's look at amplitude. Amplitude is going to be the distance from 0 to the trough, or we can go up either way, and we can see that the amplitude is 0.5 meters. Okay, so now let's look at our longitudinal wave. So here's our longitudinal wave. This is easier because our wavelength is, we can just simply take from rarefaction to rarefaction, which 0.5 to 1 means our wavelength is 0.5 meters. Let's count how many rarefactions we had in this time. So I have 1 rarefaction, 2 rarefactions, 3 rarefactions with a time of 3 seconds. So my frequency will be 1 hertz. That's 3 divided by 3. 3 divided by 3 is 1. And then we can look at our amplitude. Our amplitude here is going to be 0.5 meter as well. Let me use my eraser there. So our amplitude is going to be 0.5. Okay, so let's finish up with these properties of wave. What is the relationship you can conclude between frequency, wavelength, and energy for the electromagnetic radiation shown below? We can see wavelength here is very long. We can see wavelength here is very short. So let's look. There is no relationship. There is definitely a relationship between wavelength and frequency. As wavelength increase, so that means this line gets longer, both energy and frequency decrease. This will be your best answer. Because electromagnetic spectrum, wavelength or energy is related to frequency. So frequency decrease, energy will too. We know wavelength and frequency have an inverse relationship. So if wavelength increase, frequency will decrease, which also means energy is going to decrease. And that's for electromagnetic waves. Let's just go to the next question. Explain how sound wave interact with matter and relates to real life examples. Sound waves interact with matter in many ways. So we should remember the four main ways, which is transmission, absorption, reflection, and then we'll have diffraction, which we'll look at later. By definition, reflection is the bouncing of a wave off of a surface. So as he yells out, the wave will bounce off the wall. This is reflection, subassault, or echo. An echo is subassault, the reflection of sound off a hard object. Absorption is the transfer of energy of the wave into a medium. So as sound from this phone passes through this insulated wall, the insulation will absorb the sound. It is taking energy away from the sound wave, and the sound, less of the sound will be able to transfer through the wall. The last one is transmission. Because there is no insulation in this wall, the sound is passing through the wall. That is transmission, means to pass through. Here, the diagram below models a sound wave from a car horn hitting the wall. So here we have to do math. The incoming sound is 100%. 20%, so of that 100%, 20% is going to be reflected. So I'm going to subtract 20, and that gives us 80. That's from the reflected, that's given here. Then 70% of the sound is transmitted. So I'm going to subtract 70, and that gives us 10. So what portion of that 100 gets absorbed? We're left with 10. That means 10% of the sound must be absorbed, because we have the three transactions: reflection, transmission, and absorption. 10% of the sound will have to be absorbed, because the other 90% was either reflected or transmitted. Next question, why recording studios have foam materials on their walls? What do we want in a sound studio, which I don't have in here, is we want sounds to be absorbed, contained within this room, and for outside sounds to stay out. So, what this foam material will do will reduce noise and background noise. So I need foam material in this room. Let's go ahead and finish out with sound, hopefully. Sound waves can travel through liquid, solids, and gas. They require liquid, solids, and gas, because we know that sound is a mechanical wave. And unlike light, they cannot travel in a vacuum. So sound requires matter, solids, liquids, and gas. Sound waves, the speed of sounds depends on the density of the substance it is traveling through. or the medium that it's traveling through. The denser the medium, the faster sound will travel. So it travels fastest through solid, then liquid, then gas. So gas is the least dense material. It travels the slowest through gas. Solids are the most dense material, so it'll travel faster through solids. Let's look at the effect of temperature. Gas, a higher temperature will cause sounds to travel faster in a gas. So here's air at 0 degrees and air at 20 degrees. We can see it travels faster at higher temperatures. Solids and liquids are the opposite. Sound will travel faster through cooler solids and liquids, okay? Because the speed of a sound wave decreases because particles get further apart, okay? So the speed of a sound wave will increase as temperatures increase. In a gas, if we increase temperatures in solids or liquids, then their speeds will decrease. Let's look at these questions. So we can calculate the speed of sound. Remember, speed is equal to distance divided by time, which we have right there. So simply calculate by taking distance 30 meters divided by 5.03 seconds, and that is equal to, we can round that 5.03, we can round it to 5, and that makes it easier. 30 divided by 5 is 6. So it is equals to 6 meters per second, because we don't want any naked numbers. We need to make sure we put our units in there. Okay, let's look at the next one. Change color just to make it easier to look at. 40. And you guys will be provided with calculators during your tests. 40 divided by 6.49. And again, it might be easier to round this to 7. But since you'll have calculators, there's no need to. 40 divided by 6.49, and this will be a multiple choice question, is equal to 6. Then we'll go to the last one. 50 divided by 7.89. 50 divided by 7.89, which is equal to again is equal to 6.34. Okay, so that's easy enough. You just take distance divided by time, and I have naked numbers here, so we need to make sure we do 6 meters per second, and here we also need 6.34 meters per second. Okay, sound waves takes about 0.03 seconds to move through a material that is 10.3 meters long. So we have 10.3 meters, that's our distance. We're going to divide that by time, which is 0.03 seconds, and we will find that equals 4.5 for 3.3333, which is closest to air, so we can just simply circle air here. That's the end of this video. Sorry if it seems like I'm rushed. I'm just getting a little bit tired, but I'll catch you in the next video, inshallah. We will finish up sounds. Well, actually, we will start light and finish that up, and then we will spend some time with the writing portion. Ma salama. I look forward to seeing you in the next video.